Integral calculus. I know, it can sound pretty intimidating, right? But what if we thought about it a different way? Let's picture it as a powerful toolkit, one that lets us solve all kinds of cool problems. And over the next few minutes, that's exactly what we're going to do. We're going to build that toolkit together, step by step. So let's just jump right in with a question. You've probably spent a ton of time learning how to find derivatives, the rate of change of something. But what if you could run all of that in reverse? What if you already had the rate of change and you wanted to figure out what the original thing was?
Well, that is exactly what integration is all about. It's the process of finding what we call the antiderivative. Honestly, the easiest way to think about it, it's literally the undo button for differentiation. It just takes you right back to where you began. All right, so here's the game plan for how we're going to build this toolkit. First, we'll really lock in that whole reverse of differentiation idea. Then we'll get our basic tools, we'll move on to trig functions, then tackle some trickier integrals, and finish up with the ultimate technique, integration by parts. Let's get into it. Okay, first up, let's make sure we really see the connection between what you already know about derivatives and this whole new world of integration.
This image just lays it all out perfectly, doesn't it? We know that if you take the derivative of 2 times the square root of x, you get 1 over the square root of x. So, naturally, integration just reverses that trip. The integral of 1 over the square root of x gets you right back to where you started. But hang on a second. What's the derivative of, say, 2 times the square root of x plus 5? It's the exact same thing, right? Because the derivative of that constant 5 is just 0. And that right there is why every single time we integrate, we have to add that little plus c at the end. It's our way of saying, hey, there might have been a constant here, and we need to account for it. It's a super important detail.
All right, now that we've got that core idea down, it's time to actually start building our toolkit. These are going to be the workhorse rules, the ones you'll reach for again and again.
And here it is, tool number 1, the absolute bedrock of integration, the power rule. And you're going to love this because it's so simple. To integrate something like x to the power of n, you just do 2 things. Add 1 to the exponent, and then divide by that new exponent. That's it. Well, and of course, don't forget our good friend, plus c. This is your go-to move for most basic integrals for sure. Okay, let's see it in action. Take a look at this one, the integral of x plus 1 squared. Now, it might look a little fancier, but the rule works exactly the same. Just treat that whole x plus 1 part as your x. So, what do? We add 1 to the power, so 2 becomes 3. Then we divide by that new power, 3. Slap on the plus c at the end, and we're done. See? The pattern holds up perfectly. Okay, let's add 2 more essential tools to the kit. These are special cases, but you'll see them everywhere. The first one is maybe the easiest one in all of calculus. The integral of e to the x is just e to the x, plus c, of course. The other one you absolutely have to know is the integral of 1 over x. That one gives you the natural log of the absolute value of x plus c. Seriously, burn these 2 into your brain. They are clutch. All right, our basic toolkit is starting to look pretty good. So now let's put it to the test on some new shapes, specifically trig functions. And the real secret here isn't about memorizing a bunch of new rules. It's all about applying the patterns we already know. So here's the good news. If you already know your derivatives for trig functions, then you pretty much already know your integrals. You just have to flip your brain into reverse. You know the derivative of sine is cosine, right? So guess what? The integral of cosine is sine. You know the derivative of cosine is negative sine, so the integral of sine is negative cosine. This whole chart, it's just the mirror image of stuff you probably already have down pat. And really, this is all about spotting patterns. I mean, look at this problem. At first glance, it looks like an absolute monster, right? But let's take a closer look. We've got the secant squared of the natural log of x all divided by x. We can just rewrite that as secant squared of ln of x times 1 over x. Now, wait for it. Do you see it? We have a function, our f of x, which is ln of x. And what's sitting right next door? Its derivative. F prime of x is 1 over x. That's a classic pattern. And whenever you see that, the solution is just tangent of the original function. So tan ln of x plus c. It looked terrifying, but it was all about spotting that hidden pattern. Okay, we're getting pretty good with the standard stuff. So let's add a couple of specialized tools to our kit for those integrals that look, a little weird.
And this right here is a huge one. It's a major signal you need to learn to recognize. Anytime you see an integral with a square root in the denominator, and inside that root you have some number squared minus your function squared, a little alarm should go off in your head. That alarm should be screaming, inverse trig functions.
This specific pattern you're looking at, that is the textbook setup for inverse sine or arc sine. But, life's not always that easy. What happens when the problem almost fits the pattern, but not quite? Well, that's when you have to get a little clever and make it fit. Take a look at this example. We have the square root of 12 minus 9x squared. That doesn't really look like our pattern. But watch this. If we just factor out a 9 from under that square root, we can do a little algebraic magic and transform the whole thing until it is a perfect match for that inverse sine form. It's a great reminder that sometimes your most powerful tool isn't calculus, it's just good old-fashioned algebra. Here's another fantastic example of that exact same idea. You see this integral of this just messy fraction. It looks impossible. But hold on. Before you even think about integrating, what if we just simplify it? A little bit of polynomial long division turns that horrible fraction into a nice, simple polynomial with a little piece left over. And integrating that, oh, that's a piece of cake with our basic power rule. The moral of the story, always look to simplify first. All right, it is time. Time for the big one, the power tool, the technique you pull out of the box when you're faced with the integral of a product of two functions. This is integration by parts. Now, I'm going to be honest. When you first see the formula, the integral of u dv equals uv minus the integral of v du, it can look intimidating, but it's not some crazy magic spell. It's actually just the product rule for derivatives, but kind of worked backwards. All it is a recipe, a step-by-step process for trading in one hard integral for one that's hopefully much easier. And here is that recipe broken down into 4 simple, manageable steps. Step 1, look at your integral and decide which piece is going to be your u and which part is going to be your dv. Step 2, differentiate your u to find du. Step 3, integrate your dv to find v. And finally, step 4, just plug those 4 ingredients, u, v, du, and dv, back into the main formula. It's that systematic. Okay, let's put this recipe to the test. Let's try to integrate x times the natural log of x. None of our other tools can touch this thing, but with integration by parts, we just follow the steps. We'll choose our u to be ln of x and our dv to be x. Then we find our du and our v, plug everything into the formula, and poof, the integral we're left with is way simpler. We just follow the process, and the solution just unfolds. It really is a systematic way to crack problems that seemed impossible a minute ago. So there you have it. That is your essential integration toolkit. We started with the basics, right? The power rule, e to the x, 1 over x. Then we learned to be pattern detectives, spotting the setups for trig and inverse trig functions. We saw how powerful it is to just simplify a problem with algebra before you even start the calculus. And then we brought out the big gun, integration by parts for products. And really, that's the whole point. Integration isn't about memorizing 1,000 different rules. It's about deeply understanding a few key tools and getting really good at knowing which one to grab for the job at hand. So we've built the whole kit, from the simplest screwdriver to the most advanced power tool. The only question left is, now that you have this amazing toolkit, what cool, complex problems are you going to go out there and solve?